All right. So, like I said, so basically today we're going to cover our last lecture, which is just sort of a broad overview of the big pictures that you're of the MegaSat board that you guys are going to be building as part of your payload. Um, and yeah, so we're not going to go into detail of every individual part, but we're going to sort of look at what are the big system level blocks that make this thing up. So we are somewhat imprecise when we say MegaSat, because sometimes when we say MegaSat, we are referring to the individual board that we provide you guys. But sometimes we also refer to the entire stack of that board plus the Arduino Mega plus the GPS shield as the MegaSat. But in this case, when we're talking, at least in the context of this lecture, when we're talking about the MegaSat, we're talking about the actual board, the development board that is going to form part of your payload, which is designed to be used with the Arduino Mega, which is the microcontroller that we've been using all year. So this is a board that was actually designed here at LSU by Josh, who you may remember from some of the fall lectures, as well as some other people in the physics and astronomy electronics shop here. And it was designed as sort of the replacement for an old board that we had called the MegaSat, which was served a similar purpose in that it was a baseline student payload for teams participating in the LACES program. So all of this goes back to something called the CanSat, which was a project that came out of Stanford, developed by Bob Twigg. So he had this, basically, he had a board designed, and it was called a CanSat because it was a satellite that would fit inside of a soda can. So it was a small microcontroller board with some other sensors and ancillary equipment, so size to fit inside of a soda can. So the MegaSat was sort of the next step developed out of that. That was in the early 2000s when the program was started here at LSU. Brad Ellison and Jim Giamanco adapted that board into and expanded it some, and that's what the MegaSat was. But like it says right here, that goes back to the early 2000s. So that was it was definitely starting to show its age, to the extent where it was becoming difficult to find replacement parts to be able to build it. So we needed sorry, let me step back. The things that the MegaSat added to the CanSat was it basically added ways to interface and expand beyond the built-in sensors. So the CanSat sort of was a complete package, and you couldn't really add on to it. And what the MegaSat did was basically add some interfaces so that you could expand, add your own prototype circuits, prototyped or additional sensors and boards to that. And like I said earlier, the MegaSat goes back to the early 2000s. So I think 3 or 4 years ago now, that's when the MegaSat was designed as a replacement, a fairly extensive replacement, completely new microcontroller, and as designed to interface with that standardized shield footprint so that teams could utilize all of the hobbyist and off-the-shelf boards that are, designed to be used in the Arduino ecosystem. So the microcontroller on the CanSat, and this is what that thing looked like. So you can see that this thing is basically this far across, is as wide as a 12-ounce soda can. The microcontroller, which is the thing in yellow here, was called a basic stamp. So it was basic is because it used the basic programming language that some of you may have heard of or may be familiar with. And stamp is just what the actual microcontroller was called. There were some additional separate chips that were, like an EEPROM for data storage. And you had a modem that you would then hook up to some sort of radio transmitter. And the idea was that, you would fly this thing from a satellite and then or in a balloon, and then you could receive and send data using that transmitter. So the way that we operated the flights here in ACES is we didn't give students a radio transmitter, so we didn't need the modem. But there was a number of additions, like I said, to basically allow expansion beyond this base set. So this is what the BalloonSat was, which was for the long time the workhorse sort of central component for student payloads. Again, it used that same microcontroller, the basic stamp. You had an EEPROM for storage. I believe it was like 4 kilobytes or something like that. So it was a very limited amount of storage. It had a 4-channel ADC, which was, again, a separate chip. A voltage reference, which was part of the support circuitry for that ADC. A built-in temperature sensor and a real-time clock, and then a few LEDs that are basic, outputs of to allow for troubleshooting. And I think this board was actually used for, I want to say, about 15 years or so. So you can see right here, this is an assembled basic or BalloonSat without any of the integrated circuits installed. But you can spot a few components here, right? So you have a voltage regulator right there on the left-hand side, upper left corner. You have a DB9 connection, which is how you would actually connect. So that is a old serial connection, as in pre-USB serial port connection. And that's how you would actually upload programs to the basic stamp. The large socket in the center here, that's where the basic stamp would actually be. Off the top of my head, I don't remember which of the rest of these chips were which. You have this battery here, that's for your real-time clock, so that you can set the real-time clock and not lose your time whenever you power this thing down. But like I said, this is the past. And this is sort of, it was becoming difficult to even find replacement parts. And there was a lot of, this was a fairly limited piece of hardware for students to build payloads around. And in the intervening years, a lot of microcontrollers became much more available and easier to deal with for students. So this right here is sort of your second level. This is your block diagram of your MegaSat. This is specifically the MegaSat board itself. You can see that the Arduino is here as a component, right? Because the actual MegaSat board has to interface with the Arduino. So you can see you have a few basic Your power source here is a 12-volt battery that goes through your various regulators that distribute power to the different components. And you'll see also that that same battery provides the power to the Arduino, and the actual pin is labeled here. So that's actually through the VIN pin on the Arduino header. So that's one of the pins sort of on the, what I usually think of the left side when all of the cable connections are on the top. One thing that the MegaSat board does as part of this that's not shown here is we put in a rectifying diode in that connection. So the base Arduino doesn't have any sort of protection through that VIN pin. So if you could potentially hook your battery up the wrong way and you could damage your Arduino. So one thing that we have considered is we've put some voltage protection in there. Besides the power distribution, you'll see that you have a few built-in sensors. So there's 2 temperature sensors. We usually refer to these as an internal and external temperature, just because that's the most obvious way to use them, is one of the temperature sensors to monitor the temperature inside your payload box and another outside your payload box. There is a humidity sensor that's part of it. There is a pressure sensor. And then you have a accelerometer and gyroscope. That this combination is also referred to as an IMU, which is an inertial measurement unit. And then you have a real-time clock for keeping time. One thing you'll note is there is a logic level shifter between the real-time clock and the IMU and the Arduino. We'll get to why you need that a little bit later. And then sort of the other main component that's part of the baseline payload is the GPS shield, which is your GPS and SD card, right? Your SD card provides your onboard storage, and your GPS provides you, GPS position and time data. So once your payload is, assembled, it will actually look something like this. This is actually a previous version of the board. We recently have had to revise the pressure sensor, but this is just an idea. This isn't really a photo that you're meant to scrutinize. It's more of this is what everything looks like when it's all put together. And you can see here that this is the GPS on top of your header pins. The Arduino would be on the bottom. You can see the jumper for the actual GPS connection to get that serial working is here. You have a few potentiometers in your sensor circuits, allowing you to adjust gain and offset. And then this red thing here, that's the actual IMU. That's your gyroscope and accelerometer. So the whole thing is designed, to provide the interface between the Arduino and these sensors. So you have that standardized footprint of shield form factor where you solder the header pins in that allows you to stack shields on top of this, and the pins go all the way through to the Arduino on the bottom. Like I said, you have a real-time clock, which is actually the largest integrated circuit right here. It's a little bit hard to see because it's behind the jumpers. And then you have a battery that goes with that real-time clock that allows it to keep the time even if you disconnect the main power. You have your temperature sensors here and here. These are the 2 sets of temperature circuits. The pressure circuit is in this region right here. And then this is where your humidity circuit is. The actual sensors for these three components, you can see there are connections off the side here. So those are meant to be sensors that have decently long leads so that you can position those sensors where you want. The pressure sensor here, and this is also the case with the new, is like an 8 pin sensor. So, and also you really don't expect to contain pressure within your payload box. So you don't really need to worry about putting the pressure sensor near where you're sensing. And all of that is supplied through this connection right here. This would go to the 12-volt battery pack. So, you know, the major components that we just talked about. First, you got a real-time clock. This is the actual circuit of the real-time clock, the level shifter, and the gyroscope accelerometer. All of this is in detail that you'll want to look at as you go through the assembly manual that you're going to be using. That's the step-by-step document that tells you how to put it together. But the actual real-time clock is a Maxim real-time clock. This is the model number. You talk to it over I2C. It is capable of using the fast I2 speed, which is 400 kilohertz. Most of the I2C components you're going to run to are going to operate on this fast speed. There is one other standard speed that is higher. I believe it's called ultra fast, but usually you have to go looking for something like that. And these days, I believe it's very uncommon to find components that are slower than that. And that speed is referring to the speed of the I2C clock. And also, this is a maximum capability. You can always run since you can set that clock speed in the Arduino, you could run it at a lower speed if you wanted. So what this thing does is it gives you a temperature compensated crystal oscillation to measure time. So that means it's not going, the real-time clock should keep accurate time as long as you're anywhere within its operating range, right? You could easily, so most clocks operate on some sort of oscillator, and usually oscillators have a temperature dependence to their frequency. So the real-time clock actually has a temperature sensor built into it, and it will automatically compensate for those changes. One thing that you could do is you can actually read the output of that temperature sensor. It's, you know, plus or minus 3 degrees accurate is what they claim. But that is an additional sensor that you could pull from if you were interested. It has a backup battery that's built in that basically allows the clock to keep time and continue counting time even when you remove the main battery power supply. It gives you not just a time, but you can get year, month, day, hour, minute, second. You could also get day of the week, though that one you basically tell it what day of the week it is, and it just cycles through 1, 2, 3, 4, 5, 6, 7, right? So you could define Monday as being a 2. You could define Friday as being a 2. Usually that functionality is not terribly useful, especially because you can have the actual date, the number day. So one thing to note, though, is you do need to set this clock by writing the appropriate data to it, just like you have to set, you know, a regular old clock. I know in these days, pretty much all of us just use our cell phone, which gets the time signal from that, or we use some sort of internet connected device that will automatically set its clock. you will have to deliberately set its clock, this clock. It will operate down to a fairly low temperature, minus 40 degrees. So inside your payload box, as long as you've adequately insulated it, you shouldn't exceed that operating temperature range. So one thing to note is, like I said, you talk to this thing over I2C, and it has an address in hex of 68. And that's important because the gyroscope also uses that same address by default. So the actual model used for the gyroscope is this MPU 6050. Again, you talk to it over I2C. The main outputs that you get a acceleration or a rotation value for 3 axes, X, Y, and Z. And if you were to look at the breakout board that this comes on, you'll see little arrows labeling which way is X, which way is Y, and which way is Z. So you either get the acceleration in those directions, or for the rotation, you get how fast in degrees per second you are rotating around each of those axes. Again, and this is going to use the normal right-hand coordinate system, where if I'm rotating in a direction, if I curl my fingers in the direction of rotation, the thumb is the positive direction in the axis. So if I rotate the opposite way, you'll get a negative number. That's why you have positive and negative values for all of these rotations. And the accelerometer will read out in actual values of G rather than meters per second squared or feet per second squared. Well, each of these is actually going to read out in arbitrary ADC units that you then use whatever the range setting, the full range is, to get the value. So one thing that you can do is you can set different degrees of sensitivity. So for both of those, you'll see that you basically have 4 possible ranges, from a very low sensitivity, i.e. a very large acceleration with 16 Gs, or a very fast rotation of 2,000 degrees per second. The way that you actually get these numbers is for each axis, you will get a 16-bit number that corresponds to the 16-bit 2's complement of the value. So, but one thing that you will find as you're doing your programming and you look at the data sheets for these things, is you'll get these in an upper and lower byte that you're going to have to combine. Like I said, the I2C address for this defaults to 068. There is a jumper on the breakout board that is connected to one of the pins of the gyroscope that basically lets you set the 0 place bit of that I2C address. And by default, it's 0. So as part of your assembly, you're going to need to desolder the existing jumper connection and then resolder it to a different pad that will shift this address from 068 to 069. So that's all documented in that assembly manual, but it is something that is sometimes an issue. If you skip this step, both the real-time clock and the IMU are going to use the same address. So basically, you're not going to be able to talk to either one because they're both going to think you're talking to it. So like I said, there is also a logic level shifter. This is because both of these components use 3.3 volt logic. The Arduino, as you should be familiar with, now uses 5-volt logic. So that means you need a level shifter in between those. So the actual level shifter component is this Texas Instruments. It is a bidirectional level shifter designed specifically for I2C applications. So it's not like a generic level shifter. And the fact that it's bidirectional means that basically you have the 5-volt SCA and SD clock and data lines and the 3.3 volt, and it sends whatever's going on this side to the other side and vice versa. It goes both ways. And this thing, this chip, whenever you're dealing with level shifters with some sort of pulse signal, you really want to make sure that it's capable of the frequencies that you want it to. And since this is a chip designed for I2C specifically, it is designed to work with that fast standard. So as long as you assemble this correctly, you should be able to communicate with the Arduino through the level shifter to the gyroscope or the real-time clock. Next, sort of going through the analog sensors. Like I said, you basically have 2 temperature sensors. Just like the capstone project that we did at the end of the semester, we're going to be using a silicon junction diode as the actual temperature sensor. Since this is an actual design circuit, we're going to be a little bit more careful about it. So we're going to use a constant current source. That's what this is here, to supply a fixed current through the diode so that we can look at the voltage difference and we don't have to worry about the slight changes in the diode voltage also affecting the current going through it, which then affects what the voltage is, right? So we've eliminated that little bit of a feedback loop. So you have a amplifying circuit that has 2 potentiometers, one for adjusting the gain of this circuit and one for adjusting the offset. And the idea is, since you have 2 of these with their own independent adjustments, you can adjust those so that you can measure different ranges with the 2 temperature sensors. Like I said, we usually refer to one as an internal and one to as external, right? So you would probably want to set the range of your internal temperature sensor to be higher than your external, which is going to see that, minus 30, minus 40 degree as we go through the troposphere. But that doesn't mean you have to use those as a internal and external. You should look at what is your science goals. If you have other temperatures that are more important to monitor, you should feel free to use these 2 temperature circuits to monitor those temperatures. The humidity sensor is a Honeywell sensor. So basically it will be a linear voltage versus relative humidity output. One thing that you want to make sure you keep track of is there's going to be a little sheet of paper that comes with your sensor that is going to have the factory calibration data. And that will give you what is that linear relationship. And in particular, I mention this because temperature sensors are relatively easy to calibrate. Pressure sensors can be easy to calibrate if you have some way of either like a small, pressure cooker style vacuum chamber, or if you have like a little hand pump that you can hook up to the sensing port. But humidity calibration is a lot trickier. The usual way that you do a humidity calibration is you use various kinds of salt. So one of which could be sodium chloride, regular table salt. you make a saturated salt solution, and then you enclose the sensor within a volume with that saturated solution. But obviously most people could do the sodium chloride calibration data point, but that gives you a single relative humidity point. To do any other calibration, you need to use different salts depending on teams' lab capabilities. They may not have access to those salts, and also some of those other salts are kind of not very friendly chemicals that that there are all kinds of hazards. So if you don't have the capability of doing that humidity calibration on your own, you should feel free to use the factory calibration data, and that'll give you the input voltage to your circuit. Again, you have a circuit with two adjustments, a gain and a humidity or an offset adjustment. But this circuit is a little bit, it's different than the circuit in the temperature sensors. The final analog sensor that we've got, and this is the new sensor, is a Honeywell pressure sensor. It is a 0 to 15 PSI absolute sensor, and it is a 0 to 5 volt output. That means you should have about 5 volts out of this out of the sensor directly when you are at 15 PSI, and when you are at 0 PSI at absolute vacuum, you should have about 0 volts. So to use that capability for that full range, you don't need any sort of amplifying circuit because it's already well matched to the ADC limits. However, one thing that we have added is basically to give a high sensitivity, low pressure range. There's an second output. So the regular output of the pressure sensor goes to analog pin A0. Analog pin A1 is hooked up to the output of this amplifying circuit. And what that does is basically when you are at the very low pressures where you're not really, where you've lost your sensitivity on that 0 to 5 volt signal, you can use this amplified signal to give you a high pressure or a high sensitivity at low pressure. So that is it, sort of the broad overview of the Arduino MegaSat.